Greetings, mentors, ICA mentors. My name is Deshen Moodley. I'm an associate professor in computer science at the University of Cape Town. I'm also the co-director of South Africa's Center for Artificial Intelligence Research. My research area is adaptive and cognitive systems. Just to give you an idea of the types of environments or problems that I work on. So the idea is that you'll have some physical environment. It could also be virtual. There's sensors embedded in this environment, and there's data, streaming data being received from these sensors. The objective of the system is to monitor that physical or virtual environment, to analyze unfolding situations, to predict anomalous or situations of interest, and of course, eventually to decide what actions to make or decisions to take. So my work's been very applied, and it's been focused on applications in South Africa. So I've worked across different domains, initially in the sensor web, which is the Earth observation and geospatial domain with satellite imagery. I've done some work in the biodiversity domain, again, using data from natural history museums in South Africa, some indoor environment applications for monitoring indoor air pollution in low-income households, and most recently in the energy domain, understanding domestic electricity consumption in households in South Africa. I've also worked in the finance and domain, and also quite extensively in the health domain. And you can find all my papers on my Google Scholar web page. So just to abstract some more general problems that I'm tackling in these types of applications is these task environments could be unknown, so we don't understand them very well. They could be partially observable. They're dynamic, so the underlying process will change over time. And the observations are heterogeneous, so from different types of sensors, and noisy and uncertain. So there could be lots of erratic behavior, sensors could not be calibrated properly, and so forth. And under these kind of conditions, you need to make sense, understand what's happening currently in the environment, predict what's going to unfold in the environment, and take some decision or intervene. So continuing with the challenges, one of the issues has been interoperability, and the two issues that I'm currently working on is knowledge representation and evolution, and also the how the system needs to be designed and how the system will adapt to the new data or new sensors being added, and also as the knowledge evolves about the system we're observing and monitoring, what needs to happen in the computer system to adapt to this. And more generally, this area, I look at it as in terms of the design of complex AI systems that can deal with these challenges. So my future research is around three broad themes, and these are interlinked themes. So the one is keeping the human in the loop. So I believe that my stance is that effective communication and mediation between humans and machines are crucial for AI to reach its full potential. And this is, of course, aligned with things that are happening in the AI community. Recently, there's been a focus on augmented AI, where humans and machines work together instead of autonomous AI, where the quest is to for the machine to act independently. And I feel that if the human and AI, if that cooperation is resolved or streamlined or optimized, there's much more powerful capabilities that one would be able to unleash. So in this way, we'd augment human intelligence or human capability with machine intelligence, or the way the machine is being structured or has algorithms to reason, optimize, and to recognize patterns. The second theme is about frameworks and architectures. So this is more about the complex AI systems. How do we design these? What sorts of tools, frameworks, and architectures do we need? And one of the things we've noticed is that the AI subcommunities, like for example, the knowledge representation and reasoning, and the machine learning communities, they have different cultures, different approaches, there's different techniques. And strangely enough, or maybe not so strangely, they've largely evolved independently of each other. Complex AI systems will necessarily draw from all these different sub-areas of AI. The ones that I've worked on in the applications are ontologies, machine learning, probabilistic graphical models, and of course, you'd need optimization and search for model configuration and hyperparameter optimization and algorithm selection. So these AI systems will incorporate both these kind of expert knowledge or capturing human knowledge type approaches, which is like the knowledge representation and reasoning, and the more data-driven machine learning type approaches. And the last theme is something that we've been working on recently in my group, is about automating knowledge acquisition, discovery, and evolution. So humans are really good at acquiring new knowledge and can rapidly revise their beliefs and knowledge as they observe the environment. But the process that they use is hard to formalize and computerize, and we call this the challenges to automate knowledge discovery and evolution, in terms KDE. There have been some attempts, example, the robot scientist and the automated statistician, but this is, in my view, quite an open problem. So the current project that we are exploring in this area is to explore theories of method from philosophy of science. The traditional ones has been the inductive and the hypothetical deductive, and more recently, there's been a proposal by Haig about the abductive theory of method. So this is the just a very broad, generic type of architecture that we're working on. It's based on ATOM, the abductive theory of method, and ATOM has distinction between two high-level processes. The first one is phenomena detection, and the other one is theory construction. And in our architecture, there's some environment, complex and dynamic environment that's being observed. We're getting observations from all different senses. We would use machine learning to analyze this data and for pattern recognition and anomaly detection. And then we could identify things that are unexpected or new patterns that are emerging from in the environment, evolving in the environment. And then we would use some knowledge representation and reasoning methods. These are the ones that we've used before, but the idea is that you should be able to incorporate other AI techniques. And then the higher level, you'd have theory construction. Haig proposes something called analogical reasoning, and we've shown a weak form of analogical reasoning, but we think that that needs a lot more investigation. So this work has been, a preliminary architecture has been presented at a conference that is currently in progress. It's the German Conference on AI, KI 2021, and you can access that paper. I think in the next week it should be available on the Springer website. Thank you for listening to my talk, and I hope to meet all of you virtually. I won't be attending the workshop in October, but I hope to meet and interact with all of you virtually in October. Thank you.